So in this video, I want to talk about the three different types of charge density. So you might be wondering what we mean by charge density, and so I'll get more into that. So let's start with perhaps the simplest one. So linear charge density, right? So what is that? So linear charge density is given by lambda. And it also means wavelength when you're talking about waves and so on. So we often reuse variables for different things. But it's lambda is equal to dq over dl. So what are we talking about? We're talking about the amount of charge, the infinitesimal amount of charge over some infinitesimal length. So if I have some rod here, so lambda is the linear charge density. So it's how many coulombs of charge I have. Maybe it's 5 coulombs per meter. It's how much charge I have over the density of charge that I have over this rod. And so one little infinitesimal slice is going to be dq, and the length of that is going to be given by dl. So it's literally just how much charge do I have per unit length, and it doesn't have to be a rod either. So sometimes it might be like a cylinder, something like this, and maybe it goes on for some amount. And so the linear charge density is, again, if you imagine just slicing this into linear slices. So this is a slice. If you imagine a cylinder and you're looking at the side of it and you just sort of slice it right in front of you. So this thickness of this slice right here is your dl, and the amount of charge that this whole thing would have would be your dq. So it's you can just imagine with linear charge density, you're taking a bunch of slices and you're of charge, and you're sort of stacking them all up. Not to give you the total charge, but you're taking the density, I should say, of each slice, and sort of using that to find the linear charge density of the entire object that you're talking about. And so sometimes we'll also say, so this equation always holds. So, but if the linear charge density happens to be uniform, so by uniform we mean, like in this example, where it's the same value everywhere. If the linear charge density is just a number, then we say it's uniform, in which case this also holds true, where Q is the total charge of the object and L is its total length. So in this example, if this was, I don't know, let's say it had 10 coulombs and it was 5 meters long, if it had a uniform linear charge density, then its linear charge density would be 2 coulombs per meter, right? So this bit, the infinitesimal bit, always holds, right? Always holds. Whoa, I can't even write. Always holds. But this bit only holds if it's uniform, only holds if lambda, the linear charge density, is uniform. So there's 3 types of these. So the second one is surface charge density. So this is one-dimensional, right? You can kind of think of it like that. Length, right? So one-dimensional, you're talking about an infinitesimal length. Now we're talking about surface charge density. So surface charge density is how much charge you have per meter squared. And we represent surface charge density with sigma, lowercase sigma. And so surface charge density, and there's a pattern. So it's dq over, now it's not over an infinitesimal length anymore, it's over an infinitesimal area. So if I had some parallelogram shape here, dA would just be some infinitesimally small area, right? So this would be dA, and then dq would just be its charge. And so the surface charge density is equal to the infinitesimal amount of charge over that infinitesimal area. So again, this bit always holds. This is always true. If, however, the surface charge density happens to be uniform, again, the word uniform just means it's the same everywhere, then we also have this. So then we also have that the total charge of this, so the total charge of this guy is Q, and its total area is A. This whole area is A. And so if it's uniform, then sigma also equals Q over A. But these infinitesimal bits always work. They always are the case. So the third case, and I'll try to put it over here so that I'm not scrolling to a new page so that you can see all of them together. So maybe I'll cordon this off a little bit. So the third type is volume charge density. And so volume charge density is given by rho, which unfortunately mine just looked like a P. That's just how I write it. But this is technically the Greek letter rho. And so again, right, just following the pattern. So it's going to be dq, the amount of infinitesimal charge we have, per infinitesimal volume. So if I had some sphere here, so there's some 3D chunk of charge here. I don't know, it's not even a cube, I don't even know what it is, but it's some three-dimensional infinitesimally small amount of dq. And it has a volume of dv. So again, this part of the equation, always true for volume charge density. If the volume charge density is uniform, meaning it's given to you as a number, then you also have that the volume charge density is equal to the total charge. So this guy's total charge is Q over its volume, V. So it helps to also kind of keep in mind some of the formulas for surface area and volume. Really the only two that you need to know are for spheres. So for the surface area of a sphere, so this is for sphere. So the surface area of a sphere is just going to be 4 pi r squared, where r is the radius of the sphere. And then for volume, the volume of a sorry, this is for a sphere. I'm having a little trouble writing. So sphere, so the volume is equal to 4/3 pi r cubed. Again, r is just the radius of it. So these are handy things to keep in mind if the surface charge density happens to be uniform, where it's just some number. Otherwise, you want to use these infinitesimal parts that always hold, whether the charge density is uniform or not. So anyway, so I hope that was helpful. Of just giving an introduction to the 3 different types of charge densities, and these will become, you'll see the use of these as we start integrating various charge distributions to find the electric field due to them, because it becomes impractical to talk about a specific amount of charge. You want to be able to talk about the density of the charge density of the entire object, which is why these charge densities will come up when we talk about, they'll come up especially when we talk about the electric field created by various charge distributions. So anyways, I hope that was helpful.